Bienvenue tout le monde. Welcome everybody. We're going to have. Oops. Why do I have this book? We're going to have Paul Rosenbloom from USC. Je vais faire la présentation en français et puis brièvement aussi en anglais, et puis je passe le volant à M. Rosenbloom. Paul Rosenbloom est professeur émérite d'informatique à l'école d'ingénierie de génie à Viterbi, à l'Université de Californie du Sud USC. Ses recherches sont concentrées sur les architectures primitives, modèles des structures et processus fixes qui, ensemble, donnent naissance à un esprit, tel que le modèle SOAR et Sigma. Sigma est le modèle commun de cognition, un consensus partiel sur la structure d'un esprit semblable à celui d'un humain. C'est ambitieux, ça. Et puis, il va traiter des concepts de l'IA et des sciences cognitives telles que l'intelligence, les théories, les symboles, les architectures. La présentation est intitulée « Repenser l'hypothèse des systèmes de symboles physiques ». Welcome to the Cognitive Informatics Seminar. Our presenter is Paul Rosenbloom from USC. You've already, if you're here, you've already seen the summary, so I won't repeat it. We will be presenting the current state of the art of the general approaches to cognition, like the Newell-Simon physical symbol system hypothesis, which he will be rethinking. And with that, I pass to Paul. Paul, are you there?
Oh, yes. Hi. I wasn't sure whether you were asking me to start now, but thank you, Stephen, and good morning, everyone. So the physical symbol systems hypothesis has been around for over 50 years in AI. And since the very inception of cognitive science, in fact, one of the key papers was written by Alan Newell, the very first cognitive science conference back in 1979 at the University of California, San Diego. I happened to be there as an early graduate student, although I was a student of Alan Newell's at Carnegie Mellon. I was spending a year as a visiting grad student at the time at the LNR research group at UCSD. It also turned out to be the year that Jeff Hinton was there, I think as a postdoctoral fellow. So that was the year that the whole parallel distributed processing effort got started that ended up reinvigorating research in neural networks. In terms of this particular hypothesis, it's one that's it's been around for over 50 years, but it's been persistent, repeatedly and insistently questioned over that time, but it's never been completely replaced. So this was an attempt to rethink it in terms of what we've seen in the interim. I'll also introduce 3 flashbacks as needed and provide relevant background on various pieces for this rethinking. Here we go. So let's start with physical systems as they were originally conceived. So symbols were to be distinct patterns of the physical world. They're natural in the sense that they obey the laws of physics and are amenable to engineering, and they're not limited to what is in human minds or to what your high school English teacher might have talked about in terms of symbols in literature. They can be composed into what are called either symbol structures or expressions, and there are processes that can create, modify, reproduce, and destroy such expressions, so you can build computational systems out of them. An expression designates an entity if its use depends on the entity's nature. So it's not just a matter of a pointer, which is the way many people think of what designation is, but how that symbol is used has to depend on the structure of the entity that it is representing. You can designate internal entities or external ones. And for external entities, that provides an aspect of what's called grounding. An expression can also be interpreted if it designates an internal procedure for execution. You can think of this as being procedural designation as opposed to the normal form, which can be thought of as declarative designation. So physical symbol systems in general provide a form of universal computation, like universal Turing machines or modern von Neumann computers. So the physical symbol systems hypothesis itself was enunciated at various points during the 1970s, up into actually including 1980 and 1990. It's simple in statement. A physical symbol system has the necessary and sufficient means for general intelligent action. And by general intelligent action is meant something like human-like or human-level cognition. Please note that it's an empirical generalization rather than a theorem, so no attempt as if proof was provided. What was provided was the combination of a sufficiency argument and a necessity argument. The sufficiency argument was broken up into two pieces. One was an argument for universality. So if these are universal, then in some sense, they're capable of performing any kind of computation. So if minds are computational, then in some very theoretical sense, physical symbol systems must be capable of implementing minds. The other part of the argument was, again, more empirical. It said, given basically the success of systems to date was evidence for the sufficiency of this hypothesis. And to date meant basically up to around 1980 or so, or 76 or whatever you wanted to count it, but roughly during the 1970s. The necessity argument had two pieces as well. One was that humans appear to be such systems. So that said, well, if humans are, then that's some evidence that maybe all systems that do it must be so. And the lack of alternative approaches that were nearly as successful. That included the neural networks at the time, which were fairly primitive at that point. By 1980, we'd barely gotten the beginnings of things like the backpropagation algorithm. Here are a couple of key quotes from Alan Newell, reflecting sort of how important he felt this hypothesis was. So the first one, in my own view, this hypothesis sets the terms on which we search for a scientific theory of mind. And then even more intense, the physical symbol system is to our enterprise what the theory of evolution is to all biology, the cell doctrine is to cellular biology, the notion of germs to the scientific concept of disease, and the notion of tectonic plates to structural geology. So basically, he was claiming it was to be the core organizing principle for intelligence. I guess I can stop, given what we're saying, to relieve Stephen from some of the need to just monitor. If there are any questions at this point, I'm happy to answer them. I'll try to stop a few points and see if there are questions as well.
Not as far as I can see yet.
Okay. So, as I mentioned, there have been a number of critiques over the years. In 2007, Niels Nielsen cataloged a set of 4 of them and provided his own responses to them. That's what's on this slide. So the first one was a lack of embodiment or grounding. And again, his response here is that it's a misunderstanding of the hypothesis, as it already includes this. Part of this is this notion of designation and the way it plays a role in grounding. Part of it is how symbols internally are intended to be grounded in both perception and action. So they're not just these free-floating things. The second one was the need for non-symbolic analog processing, numeric processing, however you want to think about it. There, Niels said, include numbers, that is, make the systems hybrid. So you can think of the conventional approach of taking any random symbol system and just adding numbers to it in some way. The third was that that brain style computation or brain style is different from computational style, or brains are not computers. Again, his response is that brains are in fact computational. The fourth one is an odd one. The mindlessness of much of what happens to be intelligent behavior. And the response being that mindless constructs only yield mindless behavior, with the implication that you need more than just this. So one way to think about things like LLMs is that in fact, they are this form of mindless behavior. I think of them as being kind of extended cognitive cycles. And I'll talk about the notion of cognitive cycle a little before, but missing all the rest of what you would find in a cognitive architecture that is built around the notion of an individual cognitive cycle. So all you do is spinning out memory access in some form. In the case of LLMs, it's memory access based on a huge amount of learning, but it's still just memory access. It's not other forms of thinking. So in my view, I mean, despite Niels's responses, there are two lingering critiques that are highlighted in particular by the recent successes of neural networks. So again, there's a sufficiency challenge and a necessity challenge. The sufficiency challenge focuses on the lack of numeric processing in the physical symbol systems hypothesis. And numeric processing in neural networks can now do better on many problems. So it weakens the arguments from the success of symbolic systems. Universality still supports sufficiency. It implies that you can do numeric processing. So if you haven't thought about it, standard digital computers in the hardware are at the very bottom symbolic, and they implement numeric processing as hardware algorithms. So they implement it on top of symbolic processing. Symbolic architectures can do the same kind of thing, but it happens then at a slower rate than the base symbolic processing. So numeric processing is actually slower than bit processing inherently in hardware architectures. So even though universally is still there, this evidence by itself is weaker than the original sufficiency argument. And in fact, it gets even weaker when you think about what we've learned about cognitive architectures over the last decades. In particular, that they need numeric processing at the same timescales as symbolic processing. So that means you don't have the time to implement on top of the symbolic architecture if you're going to do what's necessary for cognition. So this is a good point for our first flashback, which will be on cognitive architectures. And any questions at this point before we get into that? Okay, so let's start with architectures more generally, and I've written a paper on this recently. So you think about them in the system context. An architecture amounts to the fixed structures and processes that are part of a system. And then to complete the system, you add a bunch of variable content of some sort. So you can trace the notion of a cognitive architecture back through computer architectures, all the way back to building architectures. And each has its own notion of what its variable content is. For example, building architectures, the variations are furniture and decor, things like that. Computer architecture, they're programs and data. With cognitive architecture, you can say they amount to knowledge and skills of various sorts. So if we focus now directly on cognitive architectures, they do provide models or hypotheses, but the fixed structures and processes that underlie a or the mind, depends on how many you think there might be. So that is the processes and structure that create memories and reasoning capabilities and learning and the ability to interact. As well as
Paul, I do have a question for you on the they mind. I meant to ask you before. Would you mind very much defining what you mean by mind so that we can decide what it is or one of things?
Yeah, I've got a slide on that later, but roughly, I mean, it's a very generic notion that a mind is a functional entity that thinks. Again, this is very vague. In natural systems, they're implemented by brains, but that's generically what I think of as being a mind. Does that help?
It sort of. And how could there be multiple ones?
Well, so every human has their own mind. That they're similar. Different animal species have different kinds of minds. Artificial systems might have other kinds of minds. So there is not necessarily just one mind that we're talking about, though often in cognitive science, when we talk about the mind, we're talking about some kind of generic human mind.
I'm understanding, but I understand that many different cognitive systems, many different minds, as many as there are in the room. But are you also saying that there are many different minds inside one cognitive system?
No, I'm not talking about society of mind like
Okay.
Marvin did. I mean, there are certainly multiple parts to an individual mind, but I'm thinking of a mind as being, I mean, each individual human or animal has a single mind.
Okay.
So the multiplicity is across organisms rather than within one. At least the way I think about it. Okay, sorry, I didn't realize that was the confusion. Okay, so say a mind must support all these capabilities, but very importantly, it's got to support the integration across them. You can't just slap them together. They have to work together smoothly, effectively, efficiently, and so on. Above a mind, then, it supports knowledge, but the architecture supports knowledge and skills, and all of that's part of kind of a complete mind. Once you have something like a cognitive architecture, it can support notions of unified theories of cognition, like Alan talked about, or models of practical minds for things like intelligent agents, or virtual humans, or robots. These examples are all from earlier work in SOAR, for example. In essence, the architecture is all about what is not learned. So it's not the content of LLM, it's the structure of it. It's, for example, the transformers. That would be the architecture of an LLM, or more generally a generative model. In his work on unified theories of cognition, one of the things Newell did was focus on the notion of time scales counting in cognition, particularly in human cognition. And he laid out this hierarchy of time scales, essentially an order of magnitude apart, all the way from 100 microseconds down at the bottom up to months at the top. And then he divided them up into bands. So we have the biological band, which is from 100 microseconds to 10 milliseconds, roughly organelles up to neural circuits. The cognitive band at 100 milliseconds to 10 seconds, what he called deliberate acts up to unit tasks, and then further up through the rational and social band. Part of the assumption was then that a cognitive architecture should fit in right here at roughly a 50 millisecond cognitive cycle time that you find in humans. So essentially at the base of the cognitive band. It might be implemented by neural technology, but again, originally it was intended to be a symbolic structure that supported the cognitive band. What we've learned, though, is that you need both symbolic and numeric processing at this time scale. So it's got to be a hybrid entity of some sort. Okay, if we switch now to the necessity challenge, here we're looking directly at neural networks. And again, humans also appear to be such systems. So they're not just simple systems, they're also clearly neural systems. And such systems provide an alternative that now works as well, if not better, on many problems to the classical simple systems. So that again weakens the necessity argument of the original, that was associated with the original physical simple systems hypothesis. You can ask what would happen if you shifted completely in the other direction and came up with something like a neural network system hypothesis. I'm just going to consider the sufficiency aspect of that here. So neural networks have clearly shown a remarkably wide range of successes. There are versions of them also that show universality. There are things like universal Turing machine. I mean, I've lost the exact neural Turing machine. Sorry, that's what they're called. But many recent very high-performing neural network systems have found it necessary to include symbolic processing of one form or another. So if you look at systems that play board games like AlphaZero, AlphaCosmos, they do include state space search, as do neural networks that do planning of any serious sort, more than just a few steps. LLMs all operate on word sequences, and various forms of neural networks, such as convolutional ones and graphical ones, all include other forms of various forms of composition in them. So this is in addition to the fact that there are contentious questions still as to whether neural networks actually involve symbols of some sort, no matter whether they're explicitly doing symbol processing or not. I don't want to get into those arguments in particular, just notice that they're still out there. So as far as I'm concerned, the overall question remains open as to whether it's possible to come up with a version that's based purely on neural networks. Sorry, was there a question?
Not for that, no.
Okay. So the alternative I'm proposing is to consider a particular form of hybrid symbol system that assumes both physical symbol systems and neural networks. And it's inspired by both the Common Model of Cognition and the Sigma Cognitive Architecture. So we'll do flashbacks on both of those in turn. Let's start with the Common Model of Cognition. It's developed an analogy to what's called the Standard Model of Particle Physics. It's an integrative model that combines electromagnetic, weak, and strong interactions and trying to be a unified model of much of physics. And it turns out it can classify all known elementary particles. It is a community consensus rather than something that's imposed or developed by a single theorist, developed over decades, and assumed to be internally consistent. But since it's a consensus, it may have gaps. There can be areas in which no consensus has yet developed, whether because there's not enough data or people just don't agree or whatever the issue is. But it still yields critical functionality for the field. It provides a cumulative reference point for progress that can be talked about within the field and across fields. And it guides efforts to extend and break it. You can often hear about recent results in physics, often tentative, saying this may challenge the standard model. If we shift to minds, and this is what I was referring to when I answered Stephen's question, I think of them essentially as functional entities that can think, and that support intelligent behavior. In humans and many animals that possess minds, they're implemented by brains. I don't think of minds and brains as separate things. I don't believe in dualism, but minds are sort of the functionality provided by the brain. So we can talk about it as a different level. In AI, minds are assumed to be computational entities, implementable by a range of physical devices. And of course, there are multiple approaches to trying to understand minds. In AI, which concerns building artificial minds, it cares most for how such minds can be built. In cognitive science, which concerns modeling natural minds, it cares most for the understanding of human cognitive processes. In neuroscience, which focuses on structure and function of brains, it cares most about how minds arise from brains, so things like cognitive neuroscience. In robotics, which concerns building and controlling artificial bodies, it cares most for how minds control such bodies. And of course, there are other ways and perspectives on this as well.
Paul, can I intervene again?
Absolutely.
You said in the prior slide that minds are things that think. That's practically begging me to ask what you mean by think.
Well, I could use other vague terms like cognition.
No, that's
so
just
thinking. So I don't have I do have a definition of intelligence. I've written a recent paper on that that's being considered by a journal. But thinking to me it's the set of things that a cognitive architecture supports, basically. So it's memory access and reasoning and using language, and it's kind of all the things that minds do. I don't have a better way of defining it on its own, I'm afraid.
It's good that you just gave a definition. You said all the things that minds do. We can substitute for minds things like people that think, and that's not circular, because doing is not circular with mind.
Okay, good.
So it sounds like you're trying to account for the capacity to do what thinking systems can do.
Yes, that's what I meant to convey by the word functionality, but capacity is a good word for that as well. Okay, so there's all these different ways of studying mind or minds, again, depending on how you want to view it. But there's a deep scientific question as to whether they'll all ultimately converge on a single model of mind. I believe this must happen for at least cognitive science and neuroscience, at least if we're focused on human cognition, because they're studying the same system. So they ought to converge on the same model, even if it's different, if it's, and still ends up being different perspectives on that same system. It may happen for naturally inspired AI and robotics if the class is abstracted slightly to include artificial minds of particular sorts. It may also include natural mind or artificial minds that end up being similar for functional reasons, although they're not necessarily inspired by the natural systems. So we can call this slightly abstracted class human-like minds, and more focuses on bounded rationality we find in humans than on the kinds of optimality that AI often focuses on. It is a broader class than naturally inspired minds because it includes these efforts that may be similar because of functional reasons, even if they're not directly inspired and don't pay any attention to how human minds work. But it's narrower than human level intelligence because it doesn't include those approaches in AI or AGI, for example, that are completely different from how we understand human minds to work. So it's trying to cut a fairly fine line between these various approaches. You can ask whether we'll get a broader convergence across the areas of AGI and robotics, for example. I don't have the answer to that. It likely depends on whether the space of intelligent systems is sufficiently unimodal so that all the minds that exist or can exist are all on one hill in some sense. So they all share key features, or whether they're in fact multiple distinct hills that can have qualitatively different kinds of minds on them. Okay, so the Common Model of Cognition concerns what needs to be in human-like cognitive architectures. It's attempting to provide an abstract community consensus. Right now, it is a consensus over many of the folks who work in cognitive architecture, but it hasn't really reached out well to a broader cognitive science community, for example, or neuroscience community for consensus. There are gaps to the extent that consensus is still lacking. And it's not a cognitive architecture itself. It's an abstract design on paper, basically. The hope is that it can yield a range of potential benefits. So coherent baselines facilitate shared cumulative progress, like with the standard model in physics. Focusing efforts to extend and break the consensus, providing a framework around which evaluation data can be organized, providing an interlingua for describing and comparing architectural approaches. And then also on the other side, providing guidance and things like extending research on individual components, interpreting experiments and suggesting new ones, and constructing intelligent applications of various sorts. We're starting to see some examples of various of these potential benefits. So the common model is built, it's fairly simple in some sense. Again, it's a consensus model. It has a procedural long-term memory for skills, a declarative long-term memory for facts or knowledge, perception and motor modules, and a working memory that essentially represents the state of the current state of the cognitive system. Global communication occurs through working memory, as you can see in the diagram, although there is a local perception motor link that bypasses working memory and allows faster interaction between those two modules. The procedural long-term memory can access all of working memory, but the other modules are all limited to interacting with buffers and to depend on procedural long-term memory to kind of relate what's going on in all those other modules through working memory. There are also 16 additional assumptions at this point. For example, that there's parallelism both within and across modules. So you can see, for example, system one behavior happening within some of what's going on here. But there's also a serial bottleneck in making decisions that's roughly the 50 millisecond cognitive cycle time in humans. So system two-like behavior, if you like that kind of terminology, is what's happening across multiple cycles. One of the kinds of things—
You can't see your cursor, just to let you know that if you point to something, we won't see it.
Oh, you don't see the cursor. Okay.
Now we do. Yes.
I won't try to point at things.
No, I was wrong. It suddenly appeared when.
Oh, if it's sitting for a while, you can't see it. But if I move it, you should be able to see it. Okay, good. So one of the kinds of things you can do with the common model is you compare architectures. Here are conventional diagrams for ACTAR, SOAR, and sigma. You may all be familiar with ACTAR and SOAR. Those are two of the longest lived and most well-developed cognitive architectures. ACTAR was somewhat more of a focus on the cognitive science side, SOAR a bit more of a focus on the AI side. Sigma is a newer architecture that in some sense is a spinoff of SOAR, but in another sense is radically different from SOAR. I'll talk a little bit more about that later. Okay, then if we look in terms of the common model, there were 16 assumptions here laid out horizontally, but structured into 4 different groups, focused on structure and processing, memory and content, learning, perception and motor. If you're looking at the color coding here, the dark green is kind of agreement, red is disagreement, blue is sort of agreement. It means, yes, it's there, but it's implemented on top of the architecture. And then forms of light green mean, yes, we agree, but we're not quite there yet. That is not completely implemented. So what you can see is that back in 93, ACTAR and SOAR disagreed with each other in a number of ways and with the common model. But by 2016, there was kind of complete agreement with respect to these 16 between these two architectures and the common model. Again, sigma is newer. It's not as completely implemented. And it also has a philosophical basis, which says that some of the things that are found in the common model are actually implemented on top of what's called the cognitive architecture in sigma. So again, it differs somewhat, but it, again, has fairly broad agreement. Some of that coming from its roots in SOAR. So one of the key assumptions in sigma, in the common model, and that relates to the overall topic of today's talk, is what I can call the hybrid CMC assumption. Declarative and procedural long-term memories contain symbol structures and associated quantitative metadata. So that means the common model is not a symbolic architecture. Its symbols can have numbers attached, and the expressions can have numbers attached. And that's true in all of the memories, basically. And it can affect a wide range of processing. So in ACTAR, for example, we see chunks with activations in declarative memory and rules with utilities in procedural memory. In SOAR, very similar, triples with activations in semantic memory. Episodic memory is a little different, and rules with utilities in procedural memory. Sigma, again, is a bit different. It's based on predicates and conditionals rather than triples or chunks and rules. Both of those have functions associated with them that are continuous valued. So predicate is a typed n-ary continuous valued relation. A conditional is a generalization of rule, also with an associated function. Essentially, it consists of conditions, actions, and things called conducts, which are kind of a smush of those two. They allow bidirectional processing, whereas conditions and actions are both asymmetric. So one of the things it allows is the direct representation of things like probabilistic graphical models within these same conditionals and predicates as you can use for rules. So you use conducts and predicates instead of conditions and actions plus predicates. So let's go into a flashback on sigma at this point. So sigma is based on 4 desiderata. Here's 3 of them. Grand unification says the goal is to model not just traditional cognitive behavior, which you can think of as central thought processes, but also key non-cognitive or peripheral, if you want to think it in those terms, such as perceptual, motor, and affective processing, motivation, personality. You want to be able to handle all of those kinds of things. Generically cognitive, spanning human-like natural and artificial cognition. Functionally elegant in the sense of a system that's broadly capable, yet simple and theoretically elegant. So if you look at, for example, in SOAR and ACTAR, you'll see lots of boxes. Those are modular architectures. And there's systems that are even much more modular or have many more modules than that, excuse me. If you look at sigma in the diagram here, that kind of shows there's a single underlying uniform layer in which the various capacities, if we want to think about it in that way, or functionalities, are all implemented as specializations and combinations over that uniform processing layer. So we'll talk a little bit about what that processing layer is. The goal here is to advance the elegance, depth, and breadth, both the science and the systems. The 4th desideratum is basically that it runs fast enough for anticipated applications, whether that is sort of AI applications or cognitive science models. So the approach is what's called the graphical architecture hypothesis. This is version 2. which is the key is combining what has been learned from decades of separate work in cognitive architectures, plus graphical models and neural networks. Version 1 just had graphical models in it. So this is realized by having a layer or two different architectures layered on top of each other. The graphical architecture and then the cognitive architecture on top of it, with knowledge and skills then being on top of that cognitive architecture. If we look at the cognitive architecture, it's based on predicates and conditionals, as I mentioned, and also a nested control structure, which I'll describe shortly. There's a processing cycle, which is, again, in humans, intended to model the 50-millisecond cognitive cycle, which has input, then elaboration phase, which is a concept from SOAR, but in here it includes perception, memory access, and reasoning, then an adaptation phase, which is an adaptation of SOAR's decision phase, includes decisions, but also includes learning and things like affective and attentional processing. And then it does output, and then it repeats that every 50 milliseconds. Down in the graphical architecture, there are extended graphical models and region tensors. I'll talk a bit about both of those, and a standard form of gradient descent learning. In terms of the cycle, it's simpler conceptually because it consists of just graph solution and graph modification. The graph solution provides elaboration, the graph modification provides adaptation. There is this SOAR-like nested tri-level control notion that starts in the inside with a parallel reactive layer. Again, you can think of this as system 1 if you want. It's a single graph or cognitive cycle, which then acts as the inner loop for a serial or iterative routine layer where you get knowledge or skill-driven action and action selection and application. That in turn acts as the inner loop for a recursive or reflective layer that yields impasse-driven meta-level processing. This maps well onto bi- and tri-level models, cognitive psychology, whether you call it automatic versus controlled, system 1 versus system 2, or other kinds of things. Models in robotics, like the 3T architecture found there, and multi-level models in emotion and causality in other particular areas. So let me stop there and ask if there are any questions.
I won't disappoint you. You talk about, we agreed that you talk about capacity, and this architecture that you're describing is meant to generate that capacity. Can I ask you in general what the Newell-Simon tradition, what its stance is on toy models of capacity versus Turing scale, and I mean Turing test scale models of cognitive capacity?
So I don't know anything in detail about that. So what I know is what I've stated already, that they believed in physical symbol systems, they believed in the universality of them in the same sense as universal Turing machines. So they felt that both were universal computational devices. So basically have the same capacity.
That's not the question.
Oh, okay.
I'm not asking about universal computational capacities, universal Turing machines. I'm talking about the Turing test, which is, the measure. It's the measure of what you agreed was when you define mind as being what the systems with thinking capacity can do. In the domain of doing, you're in the domain of either toy capacities or Turing scale capacities. And that's what I'm asking about. Not Turing tests, pardon me, not Turing machine scale. We know that.
The Turing test.
Yeah.
Okay, sorry, I misunderstood you. Yeah, the audio quality unfortunately isn't completely clear. So I don't remember talking to either Alan or Herb about the Turing test. I know the general feeling back then was that the Turing test was useful in the sense that it let you talk about tests of intelligence that didn't have to look inside the brain or inside the machine. And so the fact that it abstracted away from what went on inside was a useful conceit, essentially. But that we felt it was in some sense too easy to solve. It was both too easy and too hard, in the sense that it was way too hard for any of the kinds of systems we worked on. And systems like Perry, way back when, which was a simple chatbot back in the probably in the 60s, I think, or early 70s, I guess it was maybe early 70s, could fool people already. And therefore, in a sense, it was both too hard and too easy. Again, LLMs are clearly blowing it away in various ways, implying that either you want to say that they've passed it or you want a different kind of test. But I haven't put a huge amount of effort into rethinking that kind of a notion.
Well, performance capacity is performance capacity. And the test of whether your model generates the performance is whether it generates the performance.
Well, but that's performance. There's performance on all different kinds of problems. So the Turing test focused on one particular kind of problem, that is interaction in natural language, within the constraints of the kind of conversation it was reasonable to have. The kinds of problems AI focused on back in the 70s and 80s were sort of solving games and puzzles and things like that, or knowledge-intensive problems, the expert system kinds of problems. So the kinds of problems that were being worked on then were quite different. LLMs clearly are focused much more directly on interaction in natural language. So in some sense, you could say they are completely geared towards the Turing test, even though that wasn't the original motivation for them. So you have to look at capacity in terms of, if you're looking at cognitive science, you can talk about capacity in terms of any kind of psychological experiment, and ask how well does it, I mean, which is also external behavior, and ask how well does the system model that. You can ask whether that behavior is relevant to intelligence or not, or there is just some side issue of how human performs, which isn't relevant to intelligence. So you get into all sorts of tricky questions there. But when you're talking about capabilities, there are all sorts of ways to define what capabilities are you're trying to model, and assessing whether, in fact, you have, in fact, modeled those capabilities well.
Capacities of thinking systems are not restricted to verbal capacities. We agree on that, right?
Absolutely.
Okay.
Yes.
But the first form in which Turing introduced the idea, the methodology actually, the Turing test, was verbal. And what people are saying now, I don't want to sound like Trump, but what people are saying now is that ChatGPT either has passed or will soon have passed the verbal version of the Turing test. Where's where's all of the architecture?
So I have several ways of thinking about that. One is, I can say, yes, it has passed the Turing test, and it shows the limitations of the Turing test as a test for intelligence. Or I can say, no, it hasn't quite, because you can trip it up and make it clearly non-human if you know what you're doing. So both of those are answers, and both are true, even though they give contrasting responses. Does that make sense?
Where do they put ChatGPT in the universe of cognitive architectures?
So in my view, it's a model of the cognitive, well, it's a model of the elaboration phase within the cognitive cycle. To the extent it makes decisions, it handles part of the decision phase as well. But it's a single cycle. It's an extended cycle. It's extended and probably long in time, just as a POM-DP is. When we modeled POM-DPs in Sigma, it was within a single cycle. But given that you could make the POM-DPs as long as you wanted, it was implausible as a model of human decision-making. So it doesn't include the full cycle, and it doesn't include multiple cycles, and it doesn't include reflection on the behavior going on there. It also doesn't include the affective components, or the personality components, or the motivational components. They appear to be there in some sense, but they're not really there. They're there only because they're implied by the knowledge that the system has learned from. And so it gives, to my view, it gives an appearance of having those things without actually having any of those. So if we go back to this figure, and if you can see the mouse, I see LLMs, I mean, they're basically solving graphs, and they're doing this portion of the overall system. And they are doing essentially perception, memory access, and reasoning of a sort. of the amount that you can do within a single cycle. So system 1 level reasoning, stuff that's practiced, compiled down, automatized, however you want to think about it. It's not doing, maybe doing decisions, because it has to decide on what the next word is. That's the only form of decision it actually makes. The learning all happens beforehand. So again, in my definition of intelligence, I distinguish kind of pre-performance learning versus lifelong or cumulative learning. It doesn't do affect. There is a sense of attention in the transformers, though it's just one sense of attention. So that's kind of how I see it.
Okay, maybe we can get back to that in the question and answer period. Go ahead, please.
Okay. So related to all this, and we've already talked about this, one of the key things is that generative models, and in fact, most neural architectures seem to be missing much of this structure. Okay, let's talk briefly about graphical models. You may know about them all already, at least in the form of Bayesian networks or Bayesian models. But the key thing from my perspective and the Sigma perspective is that they provide efficient computation over multivariate functions by leveraging forms of independence decomposed into products of simpler functions. So there are Bayesian and Markov networks, Markov and conditional random fields, and factor graphs. Bayesian networks are the most familiar form. They decompose joint probability distributions into products of simpler distributions, essentially prior and conditional distributions. Factor graphs, which are what we use in Sigma, pull the functions out into factor nodes and allow the decomposition of arbitrary functions into products of simpler functions. The key thing is they provide broad capability from a uniform base. So they're effective across processing of symbols, probabilities, and signals, the uniform representation of reasoning. The processing that goes on in them can be thought of in a variety of ways. So it yields loopy-loop propagation, forward-backward algorithm, Kalman filters, the Viterbi algorithm, fast Fourier transforms, turbo decoding in signal processing, arc consistency and constraint processing, and production match, and a variety of other kinds of forms of all of the algorithms are all kind of instances of the same thing. You typically solve them via some form of message passing or sampling, and they can support mixed sort of symbolic and probabilistic reasoning and hybrid processing, discrete and continuous processing. And several neural network models, in particular forms of Boltzmann machines, map directly onto them. Sigma is based in particular on extended factor graphs and message passing. So let's talk about these extended factor graphs and how they work for neural networks. So as we've discussed, factor graphs provide efficient computation over multivariate functions and importantly provide the uniform processing of symbols, probabilities, and signals. Neural networks, of course, provide powerful learning of functions. So what if we talk about merging them? You can do that, in particular in Sigma, by extending the original notion of factor graphs. So factor graphs are a form of probabilistic graphical model. For message passing, they assume bidirectional message passing in order to get us complete solution to the joint distribution problem. So they've been extended here to asymmetric message passing, which actually it didn't have to do for neural networks because it had already done it for rule systems. It turns out neural network, feed-forward neural networks and rules look very similar in Sigma. Have to enable the appropriate nonlinearities like sigmoids. So those are implemented at factor nodes. Add separate but tied return paths for backpropagation. So you can see the standard feed-forward path here in green. There's now a backward path in red, which is parallel to it. And they're tied together for learning. And then we can reuse the existing gradient descent learning algorithm based on all the messages that are coming in to these factor nodes, the square nodes on the return path. And that, in fact, can implement exactly backpropagation. Any questions on that? Okay, let's talk briefly about region tensors. It's a particular terminology for something you might be familiar with in other forms. So it's a unified representation for continuous, discrete, and symbolic data. It enables both local and distributed representations. So at base, we have standard continuous dimensions with one dimension per variable. Each of the dimensions is dynamically partitioned into regions, and there's a continuous functions over the whole thing are approximated via piecewise linear, which piecewise constant is a special case of. So here we can see a function for the probability of a weight given a concept, where we have a discrete or integral dimension on the left and a symbolic dimension on top. And in some cases, we have a single value, or in other cases, we have a linear value of some sort. You can assign symbolic labels in two ways. So you can assign them along a dimension that essentially provides a local symbolist table, local symbol table along that dimension, or you can define, it's not really shown here, but you can define a symbol as being a pattern of values over, in fact, a whole table, which could be a vector or an ND tensor in general to get distributed representations. And we've used them, in fact, in both ways. You can think of it as analogous to implementing digital circuits by restricting an inherently continuous underlying structure. Okay, so this yields a hybrid essence, essentially of an atom, which is one of these regions with numeric metadata, which in sigma could be a linear function, but as we're going to use it in the hybrid model and it's used in the common model, it's just a single value. Okay, questions here? Okay, just quickly, so I want to talk about capabilities or capacities or whatever. It was just a very compressed version of kind of in olive green, the different kinds of capabilities that have been demonstrated across memory, problem solving, learning, mental imagery, perception, natural language, and affect, includes things like motivation as well, and some of the kinds of integrated demonstrations we've used, including various kinds of probabilistic graph and SLAM and rules and tension, curiosity from emotion, other kinds of things. I've just highlighted here some of specifically neural-related things. So distributed vector models, if you're familiar with Beagle and its ilk, holographic models, we did some work directly on that. Feed-forward, recurrent, and GRU neural networks, backpropagation as I've just discussed. So in some sense, that's part of the space of what we've been able to show in Sigma. Okay, but let's leave that sequence of two flashbacks and get back, talk about hybrid symbol systems. So again, inspired by the common model and Sigma. So we start by stripping a computational symbol down to a non-obvious essence. And there's this whole methodology I've developed for what I call essential analysis that lies behind this. So a symbol becomes an atom, or you can think of it as a placeholder, terminology Drew McDermott used for a symbol, that is indecomposable into other atoms and distinct from all others. Things like designation or representation are not part of this essence, although they were inherent parts of any literature or AI notion of symbol before. And so this is going to differ from just adding numbers to existing symbol systems, because we're not going to assume that there's a traditional symbol. There could just be an atom that doesn't designate that you have a number for. Then the various aspects of traditional symbol systems like composability, designation, and interpretability all should show up as optional aspects on a symbol by symbol basis. So symbols can have these, some won't, some can have some can have all, some can have none. So we can have a symbol, you can have composability and designation. Declarative is the traditional form, which can be internal or external. Procedural is interpretation. In contrast to physical symbol systems, some but not all hybrid symbol systems are universal. So it's like neural networks in that way. Some but not all neural networks are universal. Then we add the hybrid option to allow the possibility for quantitative metadata for symbols and expression. So that's the basic notion of a hybrid symbol system. Physical symbol systems are clearly a special case. They just include all of the aspects except for hybrid on all of the symbols. The claim here is that neural networks are another special case. So it's not like you need to have a symbol system and then you need to have a neural network system as separate things. They're two specializations of this more generic concept. So let's look at neural networks as hybrid symbol systems. So we'll do that in terms of just a simple feed-forward network for paired associates, that is for paired associate words. So nodes in the input layer are hybrid symbols that do not designate. So the nodes are these individual locations here, and they're hybrid, and there's a number there, and they don't designate anything. So that's this input layer here, but shown in terms of a vector of this sort. So they aren't subsymbolic. In this terms, they're symbolic, and they're not microfeatures either. Composability of a very limited sort yields the input vector. So it's a combination here of 2, 4, 6 symbols into a vector. The input vector itself is then a hybrid expression. It's a symbol expression with a distribution over, that internally designates the word expression, which then externally designates Alan-Newell. Okay, none of this designation is happening in the neural network. The only part of this structure down here that's here is this input vector there. So then we get to the network itself. The internal and output nodes designate procedurally. That is, they point to a procedure that does summation and nonlinear transformation. The links themselves are expressions that also designate procedurally. That is, they designate the product of the node activation with the link weight. So that's effectively how neural networks are hybrid symbol systems of this sort. Questions there?
I've lost my handle on symbol as that went on. Is your sense of symbol the same as Turing's sense of symbol? And is your sense of universality the same as Turing universality, UTM?
Universality is the same notion. I don't recall a Turing notion of symbol. My notion of symbol is not the same as Newell and Simon's notion, nor the same as you find in the humanities. It's a much more primitive, basic notion. It's just this notion of an atom that is indecomposable into other atoms and distinct from all others. It has the option of having all these other characteristics that you tend to find in computational and AI symbols. But a symbol by itself need not have any of that. And a symbol system need not be universal.
Not symbols. It's not symbols. It's symbol systems that will or will not have UTM capacity. But when you say a symbol is an atom, that makes me have to ask you what you mean by an atom.
So an atom, in a sense, is a unit that's indecomposable.
A unit
and different from other atoms. So that's this definition here is what I mean. So you can think of it as a placeholder here. It's a distinct location, distinct from all other locations. Those are kind of equivalent notions. This is not a physics atom.
Oh, I know. Yeah. Okay, sorry, go ahead.
Yeah, so it's a very, very primitive element that you can identify and distinguish from all other such. Okay, you can ask what kind of a hybrid symbol system is this neural network? It does have declarative designation for the input vector. Okay, so that's an optional aspect that exists for the input vector. It includes procedural designation, that is interpretation, at internal and output nodes and on links. And that's an optional aspect of expressions that these particular expressions have. And it includes a restricted form of composition in terms of providing vectors at levels and links across levels. Now, other forms of neural networks go significantly beyond this. So, for example, localist networks have declarative designation everywhere. I talked about compositionality in convolutional and graphical neural networks, but other forms of them also have that, including, I think, transforms. They're universal networks as well. But this particular standard feed-forward network is just as described at the top. Sorry, was there a question? Okay. All right, so here's the hybrid symbol systems hypothesis. Again, very simple, like the physical symbol systems hypothesis. It says hybrid symbol systems are necessary and sufficient for general intelligent action. It's being proposed as a replacement for the physical symbol systems hypothesis. As with it, it's still an empirical generalization. It's not a theorem in any sense. So it also has sufficiency and necessity arguments. The sufficiency argument retains the possibility of universality from the PSSH, but it said it's not all such symbol systems are automatically universal, but you can build universal ones. And it can appeal to the success of symbolic, numeric, including neural, and hybrid systems. So it is a stronger argument. In a sense, a weaker universality argument, a stronger appeal to the existing work. Necessity argument co-opts the existing human cases and the range of successes listed above for sufficiency. And asks the question really whether there are any other possibilities. I mean, is there, for example, a quantum possibility? I've seen at least one paper on quantum symbol systems. Are there such, and do they provide things that are necessary but not provide by hybrid symbol systems, even if you can't define them? Okay, conclusion. Strip down the notion of a computational symbol to an atom or placeholder. The other aspects all become optional on a symbol by symbol basis. Add the option for quantitative metadata to yield hybrid symbol systems based on ideas in the Common Model and Sigma. Show the simple neural networks are instances of such systems. Propose the hybrid symbol system hypothesis as a replacement for the physical symbol system hypothesis. I didn't talk about this, but the paper also proposes a hybrid cognitive architecture hypothesis to extend this for cognitive architectures. As you recall, physical symbol systems on their own proved to be inadequate or insufficient for cognitive architectures, at least the way we understand what they need to provide these days. And you can find more about this particular work there. Okay, so I'm open to any additional questions.
Okay, thank you very much. It's open now, even with the delay. Do you want to go?
I still need to think up on my question before.
Okay, think. Just a second, because I'm not at a loss, so I'll cover the time while you're waiting. Okay, I have a couple of questions. You said in your talk many times, you used the word interpret, and you also said this is not a theorem. I understand that. An interpretation is not a theorem. It's not even a hypothesis exactly. It's a sort of a thesis, sort of like Turing's thesis. Now, my first provocative question is, can anything be fit into the framework that you developed for symbols, for physical symbol systems? Is it just a matter of find me somebody's candidate and I'll show you where it fits into this?
Into the hybrid systems? That's an excellent question. The question I haven't thought about as much as I should have. So quantum probably wouldn't. I believe
the question is less about whether you can fit this into it, but whether when you say, can I fit it in, can I interpret it as being this? Is this non-theorem applicable to this? Is it applicable to anything that does anything?
To say it wouldn't necessarily be applicable to quantum. I don't know of other things that it's not applicable to, which you can think of as making it content-free, but I don't think it is, because it strips down the essence of what's needed here. I mean, the physical symbol systems hypothesis was weak and criticized in some sense the same way, saying, yeah, well, sort of all AI systems are like that, so you're not telling me anything. But what it does is try to formulate the essence of what's required. And so in the same sense, the hybrid symbol systems hypothesis tries to formulate the essence of what is required. And in fact says, so in the sufficiency argument, so necessity is critical there. Sufficiency, you could say, is weaker because it's sufficient in a very theoretical sense, but you clearly have to build all kinds of structure up within that. In that sense, it's trying to get out the essence of it rather than build up. I mean, a cognitive architecture is trying to tell you all the other kinds of things required to be sufficient in a fixed sense for human-like cognition. This is clearly not trying to hypothesize an architecture. That's what Sigma and SOAR and ACT are, and at a more abstract level, the Common Model are trying to extract. But it is trying to identify the essence of the kinds of systems that are necessary here. I don't know if you find that an adequate answer, but that's the best I can give at this point, I think.
I'm not going to ask you what you mean by essence, but I have trouble with it, and I think everybody has trouble with it. Do you think that the people you use the standard theory analogy with physics? Do you think that in physics, the same kinds of questions that I'm raising right now about is this hermeneutics, are you fitting it into some sort of a framework that anything will fit into? Do you think that applies also to the standard theory of physics?
No, but then the hybrid simple systems are not developed in analogy with that. That's the common model, which not everything does fit into. So hybrid simple systems are a simpler or more minimal conceptualization of which the common model fits into, but so do other kinds of things.
Okay, still waiting for somebody to brave a question here. I'm not gonna let any of the time be lost. Are you surprised by the success of ChatGPT?
Yes, that's my simple answer.
Why?
I mean, so my understanding of language models originally was that they were developed purely to evaluate the quality of proposed outputs of natural language generation and translation systems. And so they were intended to be content-free in terms of knowledge about the world, just to capture the structure of good utterances in a natural language. The fact that they implicitly capture knowledge about the world when they're learned from sentences about the world, and that if you scale this far enough, that it seems to capture and be able to express in a coherent fashion a large amount about what we know about the world, caught me by surprise.
You have a provisional explanation how just reading a lot of words in context, in text, could produce a performance like that. We've agreed that thinking, right, is what thinkers do, and thinkers can do stuff like what ChatGPT is doing, but they do it vastly differently. It's not clear whether ChatGPT is cheating in some way. How is it that with the resources that are available to ChatGPT, it can do what it can do that we can do as well?
So I'll provide a short answer to that, and then I'll get to the question I see from Sabine. So in my view, they cheat in the sense of extending out the elaboration phase or the system one phase beyond, at least from a human perspective, what a single cognitive cycle ought to be able to do by having transformers or intentional focus that can go to arbitrary length. So they can simulate what we would do by multiple cognitive cycles within a single cognitive cycle, but limiting themselves then to what can be precompiled in so doing. Okay, Sabine, your question?
It's just a follow-up question on what you just said before, because language, words mean something. And so when you said you expected this to be totally meaningless, the combination of connections between words as a former lexical semanticist, that just does not compute, right? Because there are knowledge containers.
So naively, I expected to only capture syntax, basically. So the structure of the sentences, not semantics. Now you could say, I mean, you could say I was being naive there, but that's how I thought of it. It just captured the structure of the sentences, and therefore it didn't capture meaning. I was clearly wrong.
Can I just poke back? Because I mean, you've thought about this for so long and at such an exquisite level, right? So in hindsight, if you rethink that, right, what ChatGPT is based on, a large language model, connects some kind of, let me call it representations, right? These word embedding vectors that are then sort of connected with others. It's still grounded in the words that people use, and the connections in a sentence, it's not just syntactic. In fact, the syntax is a little bit, there are certain aspects in nets that you can find, but not clearly. But the connections are in parts semantic, in part in texts, they're encoding world knowledge. Don't you agree with that?
You're absolutely correct. And I don't recall whether the early language models had these word embeddings. That wasn't part of my model of what they did, which again, just could have been my lack of knowledge. But when you think of them in terms of word embeddings, again, we've done work on word embeddings in Sigma, for example. It clearly captures semantic, word embeddings clearly capture semantics. And then you put a neural network on top of that, you're capturing more aspects of semantics. If I had been thinking about it in those terms, I probably wouldn't have been quite so surprised. I've been thinking in terms of the abstract context of a language model, which is telling you whether it's a well-formed English sentence. But even in those days, it probably captured aspects of semantics as well.
May I then, sorry, you kicked me out, Stephen, if I'm exceeding my time here, but can I?
Not at all, I love it.
Stephen's question again, in hindsight and re-evaluating your first reaction to ChatGPT and being surprised. And the thing is just, we were trained, and I'm the first person to say chatbots are just for the birds, because, you know, as an interface to something, they can't be reliable. They're cute and cool, but no. And it does perform quite excessively different from predecessors. And it destroys our thing. But if you rethink it in the context of your own sort of the common model idea or whatever, is it still necessary? You still claim it's the first cycle, it's the blue block, a single cognitive cycle that they go through?
I'm sorry, I'm not lost track of what the question was. So I do believe in my model, again, it could just be show my lack of understanding of them. My understanding is that they are kind of an evolution of a feed-forward model with self-attention and a particular compositional structure on top of that, but that functionally they are providing a single cognitive cycle, but a superhuman cognitive cycle in a certain sense, that yields some amount of what we get across multiple cycles in people, but falls short of much of what we get from multiple cycles. And it may fall short of some of what happens with us, or it certainly does fall short of some of what happens within a single cycle as well. So I see it as a superhuman in some ways and less than human in other ways.
They have deep stacks of transformers, you know.
Right. But they're all, so again, in the way I see things from the Sigma perspective, multiple levels, multiple layers of a feed-forward network are all within a single cycle. If you put too many of them, then you start to get something that's implausible for human cognition. But for an artificial cognition, there's no problem with doing that. So stacking transformers, as long as you're doing back propagation across that set of them, to me, it's happening within a single cycle rather than across cycles.
And then,
But there are all, so again, in the way I see things from the Sigma perspective, multiple levels, multiple layers of a feed-forward network are all within a single cycle. If you put too many of them, then you start to get something that's implausible for human cognition. But for an artificial cognition, there's no problem with doing that. So stacking transformers, as long as you're doing back propagation across that set of them, to me, it's happening within a single cycle rather than across cycles. what I see is that reinforcement learning is something that happens across cycles. Backpropagation tends to happen within a single cycle. Now, that may be the wrong model as well, but that's how I currently kind of view it. So if you're doing backprop across, a uniform backprop across all of these different stacks of transformers, then that's happening within a single cognitive cycle conceptually.
Well, thank you very much.
Thank you.
Thank you, Sabine. Just say your name and then
My name is Matthew Gravel.
very loud.
So I have a question based on what you just finished with, on the backpropagation that
Can you hear that, Paul?
No, I didn't quite make that out.
okay.
Yeah, you're gonna have to go near
Yeah, sure.
I don't have one here, so.
I'm just moving
Okay.
to that one. Can you hear me better now?
Yes, I can. Thank you.
Okay, so I had a question about the backpropagation we talked about directly before. So in the situation where we added back the backpropagation to the architecture to be able to do the graph modification, the learning as time goes on, like we talked about earlier at the middle presentation. I was wondering, since we are talking about propagation that would happen when not when we do the learning, but during the usage of it during the single cognitive cycle, like you were saying, how exactly do we control that backpropagation? Since as you what we learn, well, it's based on the prior knowledge, also based on the context environment, we're able to tell us, okay, this has more weight, less weight. So in a situation where we just add it directly, like a normal backpropagation to the architecture, I'm not sure how exactly you can control it and make sure that you don't break the neural network itself as time goes on.
Okay, I'm not sure I got all of that, but I think the essence of the question was, so I'm doing incremental backpropagation, that is doing backpropagation once per cognitive cycle. And it's known that if you do that kind of thing, instead of doing it properly in batches, that you can kind of destroy what you've learned in various ways. And so how do I protect from that? Is that what you're asking?
That's the gist of it, yeah.
Okay, so the simple answer is at this point, I don't do anything about that. That was just sort of a demonstration of that it was possible, not a fully developed notion of how it should be used in conjunct with all of the other knowledge and capabilities and learning to provide a stable learning environment over time. So the simplest answer is I don't have an answer for you. Sorry, it's just a part of what ought to be an overall capability. So we started with neural networks in Sigma in the late 2010s. We first did some work on the distributed holographic kinds of memories. And then I realized how you could leverage the networks in there in order to do backpropagation. And then we were able to build on top of that the feed forward to do recurrent GRUs and things like that. We had hoped to go on and do things like transformers and to use them in building more complex systems. Unfortunately, I had health issues that caused me to retire, and my group moved on and did other kinds of things. So we never got into those more sophisticated aspects of using neural networks in SOAR. In Sigma. I still confuse those terms at times.
Okay, I think everybody here was hoping, and their hope was not disappointed, that you will succeed in somehow channeling Alan Newell for these times, because we would have liked to ask him as well. First of all, do you feel comfortable in being his avatar?
It depends on the kind of question you ask, because some of the things I think I understand what he would say, other things I'll feel free to say, no, I can't adequately channel him.
Okay, we're running towards the end of our time. Are there any other questions either here or out in the hemisphere? If not, Paul, I want to thank you very much for having come. I had a few more questions left, but I don't want to exhaust you.
I'm game.
You want it? All right. I'm gonna reveal my own nakedness in this. I'm going to describe some assumptions that I've made, and you may just simply not accept them. But when I asked you what you meant by a symbol, I didn't I couldn't from your answer figure out whether you were really talking about symbol in the Alan Turing sense or in some other sense that's come since then. Mine is even earlier. I think it squares with Alan Turing, which is that
So do you actually mean Alan Turing or Alan Newell when you talk about symbols?
I was talking about Turing. No, I almost mentioned Alan Newell afterwards, but I'm really just talking about Alan Turing.
Okay, because I've never looked at, well, I've read his classical paper, but I don't recall what he said about symbols.
I think it's something very simple, and if you all you have to do is look at his description of a Turing machine and his thesis, because it was a thesis that the Turing machine captures what it is that mathematicians and logicians and computer scientists.
Oh, so you're talking about symbols on the tape of the Turing machine.
Yeah.
Symbol in that sense. Okay.
Yeah. That's as simple as my simple notion is, which is that it's an arbitrary object or shape that is manipulated according to rules that are called algorithms that operate on the shape of that symbol, which is arbitrary and which may be interpretable, but that's not a demand of computation that the symbols should be interpretable, just that the algorithm produce some sort of an output that we're interested in. And then the question is, how does that relate to words? Because in the case of ChatGPT, the symbols in question are words in that big database that it swallowed in 2021 and 2022, and in the interactions it has with the users and in what comes out of it. Because words have that same property, and more so. Words not only are arbitrary in shape and are manipulated syntactically according to rules, but they also have reference. You use designation, but a synonym of that is reference. They have reference. Apple refers to apples, anxiety refers to anxiety, justice refers to justice, symbol refers to symbol. Is your sense of symbol in symbol systems that or something different?
So that's a compound question. So going back to Alan Turing's notion, which thank you for reminding me of his use of the term. My notion of symbol may be the same. It depends on what is meant by shape. So if shape is only used to identify and distinguish, then to me that's the same as what I'm talking about, or talking in terms of a placeholder of a particular sort. If you can talk about the relationship between different shapes, then you're getting to, in some sense, substructure of the symbol. And then it's a somewhat different notion, closer to the notion of a word. So a word is a symbol. Words certainly are symbols. They're symbols that have that point to other symbols in the sense of the letters of which they're composed. They also designate meanings. So there are two types of designations there to the letters of which the word is composed and to the meaning of the word. If you think of the word itself as a symbol where the letters only are used to distinguish between different words, then a word is a symbol in the sense I'm using it. But then it has these other parts that I consider optional of designation of multiple sorts. Does that answer your question?
Well, it addresses the question. Yes, words are like Turing symbols in the sense that they're some sort of it could be any object, right? Because it's arbitrary. What matters is the algorithm, namely what is the rule for what you do with this symbol, right? That's what the algorithm provides, and the Turing machine embodies. It sort of makes it executed.
Again, classically, there are two notions of meaning, sort of the declarative and the procedural notion. The declarative one is purely a designation thing. So a word designates a meaning. Then there's the other notion, the procedural notion of meaning, which is a symbol means its meaning is determined by how it's used. And so both of those, in some sense, the designation exists in both of those forms.
there's a lot of words that you've pronounced that would take time in order for me to find out what you mean by it. I didn't say meaning, I said referent. And I took you to mean by designate the same thing that I mean by reference, namely apple. In English, apple refers to that set of things there that we call apples, right?
That's declarative designation in the way I'm
I agree, and I think declarative designation is what's at issue. The procedural one is not about meaning. We don't ask what a the is or an or is. We
but
just
it does.
want to know what to do with it.
So I guess the dichotomy I was thinking of was procedural versus declarative semantics, whereas declarative semantics based on logic and things is a designation notion. Procedural semantics, the traditional notion was the meaning of a symbol is determined completely by how that symbol is used, where use means how algorithms process it. So there's a notion that the meaning comes out of that, as opposed to that it designates in a declarative fashion. So I believe that those are both aspects of meaning.
Yeah, I haven't gotten to meaning yet.
Well, I thought that's what you're terming when you're talking.
No, I was just talking about reference and designation.
Okay.
Denotation, if you like.
In terms of reference, so yeah, that's designation, and you can designate an object, or in this case, a symbol can designate a procedure, or procedures can operate on symbols. That's certainly a possibility, and that was talked about in the original form of symbol system. That's still true for hybrid symbol systems. There are processes that operate on them.
Expose my nakedness even further. If you insist on talking about meaning, we can talk about meaning. Apple just refers to apple, but the apple is red is a proposition, and that has meaning. It means the apple is red.
Yes,
So
that would be an expression. It would be an expression that has a
well, no, but the
definition.
counterpart of the referent of an apple, which is an apple, for a proposition, is a state of affairs also in the world. Apples are in the world, and apples being red is a property of the world rather than apples being ochre.
So there's the pure active designation where you can have a symbol that designates an apple. You can have an expression that designates that an apple is red. And then you can ask about what either of those mean in some deeper sense, or whether they're true in the world with respect to a particular apple, whether it's red. So I completely agree with you that meaning is a much more complex concept than pure designation. And I wasn't trying to get into meaning here.
Okay, it's a good idea. We don't. It's a good idea that we don't, but
Okay.
it
I
lurks
probably
there.
have looser uses of that term than you do, but which also means I shouldn't get into a discussion of it with you. But
I think the fitting thing is to end on the puzzle ChatGPT, right? Which is ChatGPT doesn't have any connection with the world. It just has connections with texts, digitized texts that it swallows and it aligns and it derives parameters and it predicts next word, right?
yes, but that's not an inherent limitation to these class of models. So we know there are versions. I mean, we know there are models that can deal with images. We know, I think you can connect these things to robots, so you can connect them to perception and action. So though LLMs only deal with words and language, the technology of transformers can be applied much more broadly.
I agree. But we both agreed that we're surprised by ChatGPT.
Okay.
I think we both agree that ChatGPT, such as it is, not some future one in a robot, and not some one that's doing image processing, but ChatGPT, such as it is, which made some people say that it's passed the Turing test. It does not have any connection with things in the world. It does not have any connection with the reference of its own words. We, when we talk to it, understand and interpret it, and it makes sense, and we're surprised and we're shocked. What's going on?
So, but of course, the Turing test didn't require a connection to the world or understanding the world either. All it required is being able to fully human.
It required something a little bit more than that, Paul. He said completely indistinguishable from the performance capacity of a human. Not just say a few words, that's just Siri. Something like ChatGPT.
Right, but it was a narrow bandwidth connection to the human, just including language. So yes, it had to be indistinguishable. That is, a human even you give them the ability to talk about arbitrary things, but for some fixed period of time, during that period, you have to give the human the impression that you are a human. And so you can fake it as long as the human believes it. And so ChatGPT is the canonical faker of humanness. I think we all agree it captures aspects of humanness, but misses key parts, but that it can fool people. Even Perry fooled people, and it was extremely simple. It couldn't pass the full Turing test, and there were all sorts of competitions where people tried to get better and better at it. ChatGPT is just orders of magnitude better at it than any of those other approaches were. But yes, if you know what to ask, it'll fail the Turing test with respect to a knowledgeable questioner. But in terms of a naive questioner, it can probably pass the. So the Turing test never says it has to pass it for all people. It actually never says whether it's some individuals or what's required. At least is what I remember.
My reading
for some people.
My reading of Turing 1950 is it has to be completely indistinguishable from a normal thinking human being from any other thinking human being. It doesn't have to be a genius. It doesn't have to know the answer to every question. It just has to be able to interact indistinguishably verbally for as long as you like.
So I did not recall that part. So if that's the case, that the original test said it must be indistinguishable for any human questioner, then I would say that it does not succeed. It does much better on it than any previous system, but it does not fully pass it if that's the criterion. Because people who know how to ask questions that will trip it up could probably tell that it's distinguishable from a human.
I agree. Okay, well, thank you ever so much for coming to Montreal now. You didn't see much of it.
Thank you for the invitation.
And I'll send you a thank you email afterwards.
Okay.
Bye. Let's see.